Okay, so I was on the YouTube channel. Pardon my voice, I'm very sick right now, but I thought I'd just bang this one out. All right, so Andrew has asked a question, which I choose to interpret as how are you creating the syntax trees as you parse things? So this is in response to my last video, the live stream thingy that was a huge scattered mess, but thank you for watching, Andrew, where I created a following a textbook I have called Natural Language Processing for Prolog Programmers by Michael A. Covington, which is a good book, and I bought it used. And I believe you can actually find it online for free as a PDF through various means. I think it might actually be legal to find it online even. So how was I parsing English text for very simple sentences and creating a syntax tree? That's what I'm going to show you because those are two separate things. You can write a parser that just recognizes and either accepts or rejects a sentence in a language, or you can write a parser that does that and builds up a syntax tree. And that's the more interesting thing. So a DCG stands for definite clause grammar. I'm not entirely sure why it's called that, but it looks like this. It uses this operator, the two-dashed arrow, and you can use it to describe grammars as well as some other things too, but we're going to use it for grammars. So if I say sentence is produced by a noun phrase followed by a verb phrase. Okay, and we're just going to make the most basic grammar we can first and then add the syntax tree building. So now we need to define verb phrase and noun phrase. So a noun phrase could be a determiner followed by a noun, where a determiner could be like the or a, like the dog, a dog. And then a noun could be like cat or, oops, or noun. Let me just copy this. Or dog. Okay. Now we just need to define verb phrase. Verb phrase could be, is usually a verb followed by a noun phrase. Well, not usually, but, frequently. And now we just need to define what a verb is. A verb is also, don't worry if you're not like understanding the grammar, like what the hell is a verb phrase? It doesn't really matter. You'll sort of see what's going on here. We'll break it down. So a verb could be like the example I'm looking at, which is on the cover of this book, is chased. So we're going to be generating sentences that are like the dog chased the cat, the cat chased a dog, stuff like that. All right, so let's load this up and try it out. Alt XL. And the way you use a definite clause grammar predicate is with the predicate phrase. So you give it the definite clause, the DCG non-terminal that you'd like to start with, so sentence, and then you say what sentences can you generate from this. This is the most basic way to use a DCG. So here we go. We're generating sentences. The cat chased the cat. The cat chased the dog. The cat chased a cat. The cat chased a dog. The dog chased the cat, etc., etc. And I think there should be a finite number of these. Obviously in English you have an infinite number of sentences that you can construct because we use recursion to build complicated sentences. But this grammar can only generate this many, which is fine. Okay, so that's one way to use a DCG non-terminal. But of course, Prolog can go in reverse too. So we could say something like, hey, instead of generating sentences, can you verify that this is a sentence that conforms to this grammar? So if I say the cat chased the dog, and it says true, that does conform to the sentence non-terminal in this grammar. And you can do cool things like, hey, what are things, what are things that could chase the dog? The what could chase the dog? It's like fill in the blank. You say, oh, well, that could be a cat or it could be a dog and nothing else. So that's pretty nice. In fact, you can even say the cat chased, and then I could say like, if I use the cons operator, the bar, then I could say, hey, give me the rest of this sentence. And I'll say, oh, it could be the cat, it could be the dog, it could be a cat, or it could be a dog. So there's some fun things you can do with that. So the point is, phrase can be used in two different directions, either generating or parsing, accepting or rejecting, and sort of a bunch of stuff in between too, because Prolog is cool. So how do we build a syntax tree for this? Well, it turns out these DCG non-terminals can take arguments. So I'm going to add an argument to sentence. By default, it has 0 arguments, but I'm going to add one. And I'm going to use sort of a quoted, if you're familiar with Lisp, it's like quotation in Lisp. We're just going to build a list or a structure out of thin air, and it's going to use the functor s. So we're going to use this as just a data structure, a raw data structure in here. And I'm going to say, if you give me a noun phrase from the noun phrase, and this is going to generate errors. And if you give me a verb phrase, a VP from a verb phrase, from the verb phrase, then I will give you back a sentence that uses, oh, these should be variables because we don't know what value they have, VP. Then I will give you a sentence tree that contains the noun phrase and the verb phrase. Okay, so that'll be the output. So it's giving me an error here because we changed the signature, the arity of these two non-terminals. We need to go through and do all this to all these. So in the same way, I'm going to say, oh, noun phrase contains the determiner. Maybe we'll just call this D and the noun. And then we'll say D here and N here. And we'll sort of go over this once we're done. And then down here, we're sort of at the bottom. So we're going to say determiner. We'll use the D, just a small d for the data structure. And then I want to transmit this information along with it. This is optional. You don't have to do this. If you just want to know the structure, the tree structure, we could just say, oh, we don't care about the actual words at the bottom of the tree. But I do. So I'm going to say I'm going to put this exact same atom in here. And we'll do the same thing here, D of A, because we're using the word A here. Noun, we'll do the same thing here, and I'll use N instead of noun just to be unambiguous. Cat and dog and dog. And then we'll do the same thing for a verb phrase. We'll say VP of, it's going to be V and NP. And then here we want V, and then here we want NP. And then finally, we're going to do the same thing with verb. We're going to say build the structure V, and this will be chased, and I believe that's it. Okay, I'm back. So we've just finished setting this up. Let's test it out. So if I do make, and then if I do phrase sentence, let's tell me the sentences that you could generate, and I want the tree. So since sentence now accepts or produces, I should probably say relates a syntax tree to a sentence, we need to provide an argument here. So we'll do this, and here we go. Okay, so the first sentence, the cat chased the cat, is a sentence which contains a noun phrase, which contains as its first argument the determiner the, and then the noun cat, and here's the verb phrase with the verb and the noun phrase inside of verb phrase. So yeah, it looks like it's working, and we can keep going through here, and those just all look like they're working. Okay, so it produced that. So how does this work? Let's take a look at the simplest case, which would be either these leaf nodes, either determiner or noun. So if we do phrase noun of tree and what, we can see that the tree that gets generated is this, is noun cat, and what is the sentence cat. And of course it works for dog as well. So let's go one step up and let's do noun phrase. Noun phrase. So it's when we see up here in noun phrase, the D and the N variables, those will be, by the time we're up here, those will be this expression tree. D of the will be substituted in here for D, and N of cat will be substituted here for the N, and so the resulting tree will be this. So it's very interesting in Prolog when you have tree structures as the arguments to predicates, or in this case, DCG non-terminals. When you have expressions as the argument to those things, it's sort of like they're quoted. You can build them up and pattern match on them. Okay, so hopefully that was helpful in explaining how we're building up syntax trees in this way. And if you go back and look at the GitHub project for the grammar that I was working on in that previous video, you will see that I have, if we go to syntax, let me make this bigger. It actually got so complicated, the tree structures in here, and I was repeating myself so much, and it was getting so annoying that I wrote a macro instead of minus arrow. I called it plus plus arrow, so I'm including that macro here, and that implicitly builds up a syntax tree alongside here. So if you're interested, you can go to this link, which I'll put in the video description, and you can look at how this is implemented. I think it's a little bit of a mess in here, but that was a fun project to work on, implementing this syntax sugar macro. All right, that's all I've got to say, though. I'm going to drink some tea. Bye.